Good morning. Is the audio clear? Fine. Let us start the subject then. Yesterday we were discussing regarding the concept of boundary layer theory. We have discussed four concepts for both laminar as well as turbulent boundary layer. The concepts in sequence were boundary layer thickness, velocity profile, then wall shear stress. After that, we have seen drag force. These are the four quantities we have discussed yesterday. Today, we are starting the second part of boundary layer theory. This part actually is in some books referred to as the first part. But don't worry, either way is fine. Chali, let us start now. What we're going to start today is known as displacement thickness. Today's topic is known as displacement thickness. Displacement thickness. Very important topic. Many times 2 mark questions are appeared from here, especially in mechanical paper. In mechanical paper, 2 marks question at least thrice have appeared from this topic alone. At least thrice, 3 times have appeared from this topic alone. In civil paper also recently one question came from displacement thickness. This displacement thickness is represented by delta with a star. It is represented by delta star. Let us see how do we define this displacement thickness. I'll start with the definition. You will not be able to understand the definition initially itself. Later on, I'll explain you the entire definition. The statement goes something like this. The distance measured perpendicular to the surface by which a streamline flowing adjacent to boundary layer gets displaced in order to compensate the reduction in mass flux inside boundary layer. The reduction in mass flux inside boundary layer. Now we'll understand every part of this particular definition by taking a diagram. Okay. Definition is very important. From this definition itself, we have had questions coming in. If you understand the definition, then only you can solve the question. Let us see the diagram. Imagine there is a particular plate you are having. There is some surface you are having. Let us say on this surface, there is some fluid flowing, so boundary layer formation is taking place. Let me consider this particular point as some point O, this point as some point A. Let us say I'm having a free stream velocity approaching over here. Let us say there is some free stream velocity approaching over here. Let us say this free stream velocity is represented by u infinity. This is represented by u infinity. Suppose a streamline over here is some streamline psi 1. This is certain streamline psi 2. So I'm having two streamlines over here which are adjacent streamlines. Suppose a boundary layer formation is taking place. I'm having a boundary layer formation. Let us say the boundary layer formation is something like this. You're having certain boundary layer formation like this. One second. Some boundary layer formation like this. Okay. Now let us talk about this psi 2 streamline over here. This streamline psi 2 ideally wants to move along a straight line. So it ideally wants to move along a straight line. Let us see. This is how psi 2 wants to move. This is how psi 2 wants to move. But the question is it able to move like this? The question is it able to move like this? Now what I'm going to do is, one second, I'm going to choose only this much portion. Let us do one thing. I'm choosing only this much portion of the plate. Let us say this is the point. This is a point A over here. Okay. Let me consider the section over here. This section I'm considering over here. I know that the distance over here is known as some distance delta. The distance is known as some distance delta. Delta over here stands for what? It stands for boundary layer thickness, is it not? Fine. If this distance is delta, that means this distance also over here is supposed to be delta. The distance over here is supposed to be delta. This distance is also supposed to be equal to delta. Distance is delta. Now I'm taking a section. Let us say I have taken a section over here. This is certain section I'm choosing. Across this section, there is some mass flux flowing. Let us say the mass flux flowing is equal to m dot 1. So m dot 1 over here is the input mass flux. So m dot 1 over here is known as input mass flux. Input mass flux. Now at this particular point A, or this section A over here, there is going to be certain velocity profile. Let us say the velocity profile is going to be something like this. You are having some velocity profile, which is like this. I'm having certain velocity profile, which is like this. The velocity is reaching almost u infinity. I'm representing it by u infinity itself. So now, because of this much velocity profile, there is some mass flux crossing over here. Let us say this mass flux crossing is equal to m dot 2. So I'm representing over here m dot 2 is allowed mass flux. Allowed mass flux. M dot 2 over here is the mass flux which is allowed to flow. There is some mass flux which is input to the system. There is some mass flux which is allowed to flow over here. Now, my question to you is, okay, don't type in the answer. Think logically and answer this thing. What can you say regarding m dot 1 and m dot 2? Are they going to be equal or one is going to be greater than other? The answer is, you see, m dot 1 from top to bottom is having a velocity which is equal to u infinity. Whereas m dot 2 is having a velocity 0. Velocity, let us say something which is less than u infinity. Likewise, I'm having less than u infinity, less than u infinity. At some distance later on, I'm having u infinity. That means the velocities over here for m dot 2 are lesser than the velocities for m dot 1. So for sure, I can say the value of m dot 2 over here is less than m dot 1. The value of m dot 2 is less than m dot 1. Therefore, there has to be some difference. The difference is m dot 1 minus m dot 2, which is equal to m dot 3. And this m dot 3 over here is known as reduced mass flux. It is known as reduced mass flux. It is known as reduced mass flux. So there are three mass flux over here. One mass flux is m dot 1, which is input to the system. One mass flux is m dot 2, which is going out. But the problem we are having is m dot 2 is having lesser value compared to m dot 1. Therefore, there has to be some mass flux, which is reduced mass flux. That understanding is very important for this concept. If you understand that, rest of it is easy. If you try to imagine how much is reduced mass flux, then you can imagine something like this. You can imagine something like this. Let us say, if I was having a uniform velocity profile, I would have a situation something like this. I would have a velocity profile throughout u infinity. But you see, I'm only having this portion that is able to flow. This portion that is able to flow, this much portion is not able to flow. If you want to imagine it better, let me create a shading. You see, this portion is allowed to flow. This portion over here is allowed to flow, whereas this portion is not allowed to flow. So this is representing, this over here is representing what mass flux? It is representing m dot 3. And this is representing what mass flux? It is representing m dot 2. So you're following. If the entire mass flux was able to flow, it would have a velocity profile which is represented by this rectangle. But that is not happening. I'm having only this portion, which is something like orange, that is able to flow forward. Light blue portion is reduced mass flux. Now what happens? This reduced mass flux says that I was previously between psi 1 and psi 2. I should again be between later on between psi 1 and psi 2. So this m dot 3 over here is going to push this streamline upward. Excuse me. M dot 3 over here is going to push the streamline. Which streamline? This is psi 2 ideal. It is going to push psi 2 ideal upward. When it pushes psi 2 ideal upward, then psi 2 is going to take a particular path. Let us say psi 2 over here is going to move something like this. This psi 2 is getting displaced by certain distance. Please observe over here. Psi 2 has got displaced by certain distance. How much distance is psi 2 get displaced by? Psi 2 got displaced by certain distance, let us say delta star. Delta star. And after this psi 2 has got displaced, the velocity profile over here is going to be a uniform velocity profile. A uniform velocity profile. Now m dot 3, which was not able to move from here, it has pushed psi 2 like this and it is moving over here. This is what m dot 3 is doing. M dot 3, which is not able to flow across this particular section, the section over here, it is pushing this psi 2 up and then it is moving in this particular direction. Now let us look at the definition. What is displacement thickness? It is a distance measured in the direction perpendicular to surface. Look at the distance over here. It is measured in the direction perpendicular to surface. What distance is it? It is a distance by which a streamline which is flowing adjacent to boundary layer. Now you see in this diagram, this is boundary layer. The adjacent to boundary layer streamline over here is Psi2 streamline. Psi2 is a streamline flowing adjacent to boundary layer. It is getting displaced. Why is it getting displaced? Because it is getting displaced in order to allow the mass flux which got reduced inside the boundary layer. Inside the boundary layer, some mass flux m dot 3 was not able to flow. It demanded some space to flow. For that particular reason, m dot 3, it has pushed the streamline up. You see over here, these black arrows over here are showing m dot 3 pushing Psi2 up. When m dot 3 has pushed Psi2 up, then Psi2 is creating some room for m dot 3 to flow. The height of that particular room for m dot 3 to flow is known as your delta star or displacement thickness. I hope this is clear to all of you. This is a definition of displacement thickness. Now, once we have understood this particular thing, I'm not going for the derivation. I'm just looking for the formula for displacement thickness. Some of you, I see, it seems, have come late. Okay. So look at the formula for displacement thickness. The formula for delta star has to be equal to integral 0 to delta 1 minus u upon u infinity times dy. U over here is this particular velocity. This velocity is u. U infinity over here is this particular velocity that is equal to u infinity. Just understand one thing, that whenever you're having a boundary layer formation, because of friction, some amount of mass flux will not able to flow. That mass flux is known as m dot 3. I'm calling it as reduced mass flux. I'm calling it as reduced mass flux. That reduced mass flux demands some space to move. That space to move is basically created from here. It pushes the streamline flowing adjacent to boundary layer, and then it moves like this. Now someone is asking me, in between over here, there can be one more streamline. Accept it. For example, let me create a duplicate. 1 second. Imagine if you are looking for a streamline over here, for this streamline. If you are looking for this streamline, then you have to look at this particular section. This streamline will move something like this. It will have its own displacement thickness. The displacement thickness over here is going to be this delta star. Likewise, every streamline will have its own displacement thickness. Every streamline will have. Okay. I am taking a particular section, and for that section, I have defined something like this. As such, every streamline will have. In between Psi1 and Psi2, there can be infinite intermediate streamlines. Even they will have their own delta star. Even they will have their own delta star. Fine. So this is the formula for your delta star. You can take a snapshot of this particular slide. This understanding of delta star is very important. Okay, very good. What is the path of Psi1? What is the path of Psi1? Someone is asking. Regarding Psi1, please remember Psi1 will get stagnated at point O. Psi1 is over here stagnation streamline. Psi1 is stagnation streamline. Psi1 over here is stagnation streamline. Fine. See, for a given velocity profile, remember this thing. The value of delta star upon delta has to be equal to a constant. For example, if you calculate this thing, you will be seeing, if you calculate this thing, delta star is equal to integral 0 to delta 1 minus u by u infinity into dy. You will get delta star in terms of delta. You will get delta star in terms of delta. So let us say you are getting delta star is equal to something times delta. If you are getting like this, that means the ratio of delta star upon delta has to be a particular constant. You will see all these things once you start doing questions. Chaliye. After having taken this down, I hope you have taken this down. In your rough book, whatever book you are having right now, okay, whatever book you are having right now, just mark this particular formula. Write down this particular formula. You're supposed to memorize it. You're supposed to memorize this particular formula. Now let us do one thing. We will apply this particular formula in some questions. Look over here. Let us apply this particular formula in a question. All your questions you'll understand now. Look over here. There's a particular standard question that I'm addressing right now, which I wanted to give as homework. But since you're asking me these many questions, I will put up that question and from there we'll clarify your doubts. The question is, we know of a particular velocity profile we have seen yesterday in turbulent flow, which was given by nth power law. That velocity profile is saying the value of u upon u infinity is equal to y by delta whole power 1 by n. Whole power 1 by n. My question is, find the value of delta star upon delta in this particular case. Delta star upon delta is equal to how much? This is how questions come in examination. Okay, as a matter of fact, in civil examination recently, the value of delta star upon delta was asked for 2 marks, and the velocity profile they asked it for was u by u infinity is equal to sine of pi by 2 into y by delta. For this particular velocity profile, they asked the value of delta star upon delta. Okay, but I'm asking for this thing because the result you have to remember. The result is a very standard result. You have to memorize that particular result. Chaliye, let us start this thing. I'm having u upon u infinity is equal to y by delta whole power 1 by n. This is the velocity profile. I want to find out the ratio of delta star to delta. Okay. Now, I can say the value of delta star has to be equal to integral 0 to delta 1 minus u upon u infinity times dy. This is the formula we are having, which implies delta star is equal to integral 0 to delta 1 minus, in place of u upon u infinity, I can write down y power 1 by n upon delta power 1 by n into dy. Let us integrate this thing. Integral of 1 dy is basically integral of 1 dy is equal to y. So I'm having over here y minus integral of y power 1 by n dy is going to be equal to y power 1 by n plus 1 divided by 1 by n plus 1. Not to forget, I already have over here delta power 1 by n. This is the entire value of the integral. Now I have to put from y equal to 0 till y equal to delta. This value I have to put from y equal to 0 till y equal to delta. Now let us put in these values. If I put at y equal to 0, I'm going to get 0 only. So there is no point of putting the lower limit. Just apply the upper limit. If you apply the upper limit, you're going to see delta minus. You're going to have delta power 1 by n plus 1 divided by 1 by n plus 1 into delta power 1 by n. This is the value I'm having. Now you see delta power 1 by n and delta power 1 by n cancel off. If these cancel off, I'm going to get from here. Delta star has to be equal to, delta is common. I'm having 1 minus 1 upon 1 by n plus 1. I want delta star upon delta. So I can say delta star upon delta has to be equal to this much. Now what is this 1 minus 1 by? Now this value I can write as n plus 1 divided by n. N plus 1 divided by n. So this is equal to 1 minus n upon n plus 1. What is this going to give me? If you calculate this thing, it is going to give me delta star upon delta is equal to how much? It is now going to be equal to 1 upon n plus 1. This is the answer you are going to get. It is a very standard result. You are supposed to remember this result. Whenever u by u infinity is equal to y by delta whole power 1 by n, that time delta star upon delta is supposed to be equal to 1 upon n plus 1. That is a standard result we are having. Now, let us understand the significance of this particular result. I'm going to create two conclusions from this particular result. Two conclusions I'm going to create. Look at the, I hope all of you have done along with me. Okay. I can't emphasize every time to do questions along with me. If you have interest, you will do it anyway. Now, look at the significance of this particular result in the next slide. Look over here. I have seen that the value of delta star upon delta is equal to 1 upon n plus 1. So one thing I generally see is, you see, delta star value should be always less than delta. So first conclusion I can come to is the value of delta star is going to be less than delta. The value of delta star is supposed to be less than delta. Why is it so? It is a logical conclusion. You can look over here. You see, delta was the distance required for whom m dot 1. Please understand this thing. Delta was the height for whom to flow, m dot 1 to flow. And delta star is the height required for whom to flow, for m dot 3 to flow. Delta star height was required. Okay. Now you see who is greater, m dot 1 is greater or m dot 3 is greater? For sure the input mass flux is going to be greater. You see over here m dot 1 is greater. If m dot 1 is greater, that means the height required for m dot 1 to flow is going to be greater. The height required for m dot 3 to flow is supposed to be lesser. So for sure, since m dot 3 is lesser than m dot 1, for sure delta star has to be less than delta. So first conclusion I can draw is delta star is less than delta. Second conclusion, many times in examination they are talking about linear velocity profile. They are talking about linear velocity profile. Let me write full form otherwise. Linear velocity profile. Now what is linear velocity profile? If you recall, linear velocity profile is given by u upon u infinity is equal to y by delta itself. U upon u infinity is equal to y by delta. This is linear velocity profile. So basically, if I compare this with this particular case, u upon u infinity is equal to y by delta whole power 1 by n, that means this velocity profile is u upon u infinity equal to y by delta whole power 1 by n, where n is equal to 1. Where n is equal to 1, is it not? This is what is linear velocity profile. Acha, we have developed a conclusion over here. The delta star upon delta is equal to 1 by n plus 1. So I can say for this particular velocity profile, delta star has to be equal to delta upon n plus 1. N plus 1 means 2 over here. Delta upon 2. Let us try to create a logical conclusion now. We have seen delta star is half of delta. Let us see a logical conclusion now. Imagine I'm having a plate. Imagine there is some fluid flowing over here and there is some boundary layer formation taking place. Boundary layer formation taking place. Let us say I have chosen a particular section. I have chosen a particular section. Suppose I'm having over here some velocity profiles u infinity, and this distance over here is equal to delta. This is psi 2. This is psi 1. Psi 1 is stagnation streamline. It can't move any further. Psi 2. Ideally, psi 2 wants to move like this. Ideally, psi 2 wants to move like this. But we know that psi 2 has to get displaced. Psi 2 is getting displaced. So this over here is psi 2 ideal. And this over here is psi 2 actual. Psi 2 actual. The distance it is getting displaced by is equal to a distance known as delta star. Now look over here. The velocity profile is linear. That means over here I'm going to have this velocity profile. This is u infinity. This is delta. So this is the velocity profile I'm having. Please understand this thing. Mass flux m dot 1. Mass flux m dot 1. It corresponds to this particular rectangle. Is it not? Mass flux means what? Density. Okay, let us say it is constant into area. Area over here is equal to this height multiplied to width perpendicular to your screen multiplied to velocity. Velocity is equal to throughout u infinity. So basically, density into area means delta multiplied to width perpendicular to screen is capital B multiplied to velocity u infinity. Now you see density, let us say, is constant. Density, let us say, is constant. Width perpendicular to screen is, let us say, constant. So m dot 1 is corresponding to what? It is corresponding to delta multiplied to u infinity. So basically this rectangle over here is representing my m dot 1. M dot 2 over here is how much? Now look over here. Same height I'm having, same base I'm having, but I'm having a triangle. You see, this is also u infinity, this is also u infinity. This is also delta, this is also delta. That means I'm having over here a triangle. I'm having over here a triangle. That means m dot 1, let us say something. M dot 2 is exactly half over here. So if I was pushing in this much of rectangle from here, the output I was getting was this much only. I put a rectangle, I got output which is equal to what? Half of rectangle, I got output. Now, if I ask you how much is the mass flux that got reduced, how much is the mass flux that got reduced? So what will you do? You will complete this rectangle. You will complete this rectangle and you'll say this is basically representing my m dot 3. This is basically representing my m dot 3. This is the amount of reduced mass flux I'm having. I'm having this much amount of reduced mass flux. Now, what should this mass flux? You see, this mass flux is basically saying previously m dot 2 and m dot 3 combined were equal to m dot 1. We were inside previously. Both of them were between these two streamlines. He is saying I was initially also between these two streamlines. Later also I should be between these two streamlines. So what he is doing, he is not accepting to be reduced. He is saying I will push this side to ideal upward so that he creates some vertical distance so that I am allowed to move. And the luxury I'm having is I can move over here with uniform velocity profile because I am beyond boundary layer. This flow over here is what? Beyond boundary layer. So this over here is m dot 3. So m dot 3 over here. One second. M dot 3 over here, which could not flow from here, it has moved over here. Now, logically, you think logically that m dot 2 and m dot 3 are exactly, in this particular case, half of m dot 1. If both of them are half of m dot 1, if this m dot 3, which is a triangle right now, which is a triangle, wants to shape itself in the form of a rectangle of same base, what height does it require? What height does it require? It requires exactly half the height of this triangle. Half the height of this triangle means what? Delta by 2. I hope you are following all these things. I hope things are clear that m dot 2 and m dot 3 are individually less than m dot 1. Combined, they should be equal to m dot 1. M dot 2 is basically which is allowed to move forward. M dot 3 is not able to move forward. So M dot 3 is not accepting that thing. He still wants to move forward. The only way out for him is push this streamline psi2 up. So that psi2 is creating some kind of distance. The distance is our subject right now. The distance is known as m dot 3 over here. Okay. Once he sees the distance m dot 3, then he can move. The distance is delta star. Sorry, the distance is delta star over here. See, now listen to me. There are some decent questions. There are some questions which I can't answer. Why do I keep class at this time? We do not decide our class. Class is decided by the academy. We are supposed to come at that particular time. Some questions are very good questions. Someone has asked, will the value of delta star upon delta be same? Very good question. Delta star upon delta is going to be constant for a given velocity profile. Given velocity profile. For example, linear velocity profile, half, always half. Sinusoidal velocity profile, something will get. Let us say 2 by 3, example say 2 by 3. That will be constant 2 by 3 every time. Okay. As velocity profile changes, delta star upon delta, of course, is going to be changing. Okay. When are these things going to happen practically? You are going to see now. These things are going to happen practically. Applications are also there. Actually, you can take down this particular slide. This is regarding the concept of what? Displacement thickness. It is still not finished. There is an alternate way of understanding that is also important. From there also 2 mark questions have come. Chaliye, quickly take this down. Take this slide down. Okay. As far as linear velocity profile is concerned, remember this result. The result is delta star has to be equal to half of delta. Okay. Now, many times questions will come in examination. Okay, I'm talking about previous examination questions only, where they will ask you how much is the value of m dot 3. They will ask you how much is the value of m dot 3. Always try to develop m dot 3 from here. From here. So if someone asks you, write the formula for m dot 3. Never choose m dot 3 from here. Never choose to write the formula of m dot 3 from here. Always choose to write the formula of m dot 3 from here. Both of them are correct. This is also correct. This is also correct. But never choose to write from here. Because writing from here will be complex, but writing from here will be simple. For example, what is the formula of m dot 3? Density into area multiplied to velocity. Let us look at density. Density means rho. Area. What is area? Area over here is this height. This height, all of you know what is this height? Delta star. Multiply to the width perpendicular to paper. What is the width perpendicular to paper? It is equal to capital B. So area over here is delta star multiplied to capital B. Multiplied to velocity is equal to over there u infinity. Now, why am I saying never write the formula from here, write the formula from here? The reason is, in this particular region, the velocity of m dot 3 everywhere is a non-constant value. देखिए यहाँ पे कितना है? कम है. यहाँ पे कितना है? Velocity for m dot 3. Something more, something more, something more. It is u infinity over here. It is a variable value. That is why never choose to write down m dot 3 from here. Always choose to write m dot 3 from here. Are you following this thing? I hope you are following. Okay. So there will be many times questions coming up to you regarding the value of m dot 3. So you are going to prefer this particular formula. After writing this particular formula, what will you do? You will replace delta star. You will replace delta star. You will see that delta star has to be some value times delta. So in place of delta star, you will put something times delta. Something times delta. That something you'll have to find out. That is your headache. You'll have to find out that something. So you'll have density times something times delta multiplied to B multiplied to u infinity. From there you are going to get m dot 3. Okay. All these things you'll be seeing in a question, that is question number 7, chapter number 10 from your book. Okay. You know where to find the question. Question number 7, chapter number 10. I'll look for the question along with you. You can take a snapshot quickly of this particular slide. Be very quick, please. One moment, please. Don't ask any questions right now. You see, I'm telling you, I was not taught like this. I'm telling you, if you concentrate, you'll understand everything. I'm seeing to it, everything is becoming clear as far as I can understand. Okay. The problem is the concept of boundary layer theory, you people do not touch also in your college. Let us look at that question. Yes, this is the question I'm having. The question is the question you see over here. One moment, please. Look at the question. Question number 7 says figure shows below air flowing at 30 meter per second over a flat plate of unit width. Laminar boundary layer exit velocity distribution is linear. He's saying linear velocity distribution. U upon U infinity is equal to y by delta. Okay. He has shown the diagram. Same diagram what I have drawn. Okay. These things over here. Look at the cursor. These things over here are your input. These are your input. This is your output. M dot 3 he's not showing over here. Then he's saying section CD is located certain distance x downstream. This is section CD over here, located at some distance downstream. ठीक है. Where the boundary layer thickness delta value is equal to 1.5 mm. Accepted. Mass density of air is 1.2 kg per meter cube. Mass flow rate across BC. Look at section BC. This is section BC. How much is the mass flowing across this particular section? He's asking. Tell me, just type and tell me, what is this mass flux known as in our nomenclature? According to our terminology, this mass flux is which mass flux? Please just type that much to me. Mass flux is not accumulated inside, please. Very good, very good, very good. All of you have answered. It is m dot 3, reduced mass flux. Okay, it is reduced mass flux. This is basically allowed mass flux. Whatever is the velocity profile allowed, that is allowed mass flux. Whatever is the remaining velocity profile which is not allowed, that is reduced mass flux, which is moving from here. Therefore, it is m dot 3. Chaliye, you take the if you want to take down the snapshot of this particular question, let us start the question. He's asking me the value of m dot 3 over here. Similar kind of question was asked in GATE examination also. Chaliye, look over here now. I am looking for question number 7. Question 7, chapter 10. Chapter 10. So he's asking me regarding the value of m dot 3 is equal to how much? M dot 3 is equal to how much? I know only one formula. I told you whenever you are asked about m dot 3, you will write only one formula. M dot 3 is equal to how much? Density into area into velocity. Density is density. Area is equal to delta star times b, and velocity is equal to u infinity. Velocity over here is equal to u infinity. Acha, once you have found this particular thing, now for a linear velocity profile, we know for linear velocity profile, he has given me linear velocity profile. I know that the value of delta star has to be equal to delta by 2. Delta star has to be equal to delta by 2. So if I put in place of delta star delta by 2, I'm going to have over here m dot 3 is equal to density into delta by 2 multiplied to b times u infinity. B times u infinity. You know all the values. You know all the values. This is equal to density is equal to 1.2. Delta value is 1.5 mm, therefore into 10 power minus 3 by 2. Per unit width, B is equal to 1 unit. u infinity is equal to 30. So this answer you will get will be kg per second. This answer you'll get is kg per second. You can find out this particular value of kg per second. If he wants kg per minute, I think he wants kg per minute over here, then you will multiply this particular answer with 60, then you are going to get the answer in kg per minute. Chaliye. Okay, many of you are given me correct answer. 1.62 kg per minute is the answer. 0.027 kg per second. Let me write like this. 0.027 kg per second or 1.62 kg per minute. In mechanical paper, this particular type of question has appeared in examination for 2 marks. For 2 marks, this kind of question has appeared in examination. Only difficulty was over there the velocity profile was not linear, it was parabolic velocity profile, and for that we do not have the formula. You have to derive the particular value. For that we do not have the value of delta star already defined. You'll have to develop the value of delta star over there. Okay, he will give you, for example, let us say u upon u infinity. Let us take one question: sine of pi by 2 into y by delta. Get me the value of delta star over here. Delta star is equal to, what is the value over here supposed to be? Please find this out. Please find out this particular value. Delta star is equal to something times delta. Find out this particular value, please. This was a 2-mark question in civil paper. Shall you try this thing? Delta star is equal to something times delta. What is that something I'm supposed to write over here? I can write down delta star is equal to integral 0 to delta 1 minus u upon u infinity times dy. So delta star is equal to integral 0 to delta 1 minus u upon u infinity is equal to sine of pi by 2 into y by delta times dy. So delta star is equal to how much? What is integral 1 dy? That is going to be equal to y minus integral sine of pi by 2 into y by sine of pi by 2 into y by delta is going to be equal to how much? Integral sine. Yes, please. Very good. Someone got the answer. 1 minus 2 by pi. Very good. So this is going to be equal to how much? It is going to be equal to cos of pi by 2 into y by delta whole divided by pi by 2 delta. Okay, this is a value. And where is your y ranging from? Y is equal to 0 to y is equal to delta. Y is equal to 0 to y equal to delta. Right? So what are you going to have now? One second. 2 delta over here. Actually, if you put in the values, you are going to have, when you put y equal to 0, you're going to have delta star is equal to, this will be delta minus this value is going to be equal to how much? Two delta upon pi you are going to get this value. So this is equal to delta multiplied to 1 minus 2 by pi. This is a value delta star. Can you give me the numerical value of this thing? 1 minus 2 by pi. How much is 1 minus 2 by pi? Sorry, this is supposed to be plus over here. Yes. 0.3633. So this value will come out to be delta star will come out to be 0.3633 delta. Is it? Check the value. Okay, fine. So these kind of questions appear in examination. Chaliye, let us move further. Now there is an alternate way of understanding. There is an alternate way of understanding this displacement thickness. This alternate way also is important. From there also I'm going to take a particular problem. That problem will be slightly difficult. It has appeared only in mechanical paper, but still we'll try to see that particular question. Alternate approach. 1 second, please. Alternate approach. Please concentrate on this thing. Displacement thickness, again we are discussing, but this time around it is alternate approach. Alternate approach. Now look over here. Again I'm taking that particular plate. Imagine I'm having a particular plate. Suppose this is a plate I'm having. I have a velocity profile coming in over here. In front, I'm having some velocity profile coming in. Let us say this is a velocity profile I'm having. This over here is u infinity. This over here is u infinity. This, let us say, psi. This is psi 1. This is psi 2. Let us say psi 1 and psi 2 I'm having. Let us say there is some boundary layer formation taking place. A boundary layer formation is taking place. Ideally, psi 2 wants to move something like this. The ideal path of psi 2 is something like this. This is how psi 2 ideally wants to move. 1 second. One moment, please. So if I write over here, this is representing psi 2, but it is ideal. Psi 2 ideal. Okay. But what is happening? Ideally, it wants to move like this, but it is not able to move. One minute, please. It is not able to move. So what is happening? It is going to get displaced slightly. It is getting displaced slightly, and it is moving something like this. It is moving something like this. We know that this distance over here is known as delta star distance. This distance over here is known as delta star distance, and we know that this distance over here is known as delta distance. This is delta distance. This is psi 2 actual. Psi 2 actual. Till here everyone knows this. Now we are going to make some imagination. Whatever I'm writing over here is not happening in reality. It is imagination. I am imagining that the way this psi 2 has moved exactly in a parallel fashion, I'm imagining that psi 1 also is getting displaced. I'm imagining psi1 over here is getting displaced exactly in parallel fashion. So let us say this is psi1 imaginary. Imaginary. So if I ask you how much is this distance going to be, how much is this distance going to be, you would say it is again equal to delta star. Again equal to delta star, is it not? If both of them are going to be parallel to each other, for sure, whatever is the displacement for psi2, same has to be displacement for psi1. Now I am going to think that in this particular region, I'm going to imagine that there is no flow taking place. In this particular region, I'm imagining no flow taking place. No flow region. This is no flow region. Then what happens? I will think if psi1 also got displaced up, psi2 also got displaced up, entire mass flux is moving with uniform velocity profile over here as it is. Entire mass flux is moving with uniform velocity profile as it is. And this distance is again going to be equal to how much? This distance is again going to be equal to delta. So basically, I'm imagining that if my mass flux, present mass flux is this mass flux is m dot 1. If my mass flux m dot 1 wants to move as a uniform mass flux again, if it wants to move as a uniform mass flux again, how much distance perpendicular to plate should it sacrifice? Should it sacrifice means it should not have any flow taking place over there. That particular distance perpendicular to the plate is known as delta star. Please understand this thing. Hope you are following. You see, my mass flux m dot 1, I'm imagining, initially was having uniform velocity profile. Again, I wanted to have a uniform velocity profile. If I again wanted to have a uniform velocity profile, he should sacrifice some portion of the flow. He should sacrifice some portion of its actual flow. देखिए, actual में over here flow is taking place. Actual में over here flow is taking place. This is imaginary part. So I'm imagining how much flow region should it sacrifice so that later on it is having uniform velocity profile. The distance perpendicular to the plate is known as your displacement thickness. This is one more idea, very, very important idea for displacement thickness. I hope you are following this thing. Please understand again, psi1's motion is imaginary, no flow region is imaginary. This is not actually happening. This is one more way you can think what is displacement thickness. The mass itself is getting displaced up. Mass itself is getting displaced up. By what distance? Delta star. So that if the mass is getting displaced up, it is having the same velocity profile or it is having a uniform velocity profile just the way it was having previously. Okay. Now one more step further we are going. Okay. All these things actually, if you study initially, then it will be better clear to you right now. If you're seeing this for the first time, you will find it slightly difficult. Okay, but don't worry, I'm going slow only for you. One more thing I can imagine over here. Is yeah, Shritij, you can imagine that way also. The fluid is present, but there is no motion over there. Now, if mass flux is moving up, relatively the plate is supposed to move down, is it not? I can say like this, if mass flux is moving up, relatively the plate is supposed to move down. Imagine if I would displace the plate down by a distance delta star, then the mass flux would move as it is. Just imagine, I am pushing this plate down by delta star. Everywhere, whatever is the delta star, by that much distance, I am putting the plate down. Imagine the plate is coming down over here. It is getting displaced down by delta star. Then this mass flux, without any disturbance, would move as it is. Would move as it is. From there, we are getting another definition. The definition goes something like this. The distance measured perpendicular to plate. The distance measured perpendicular to plate by which the plate should be displaced. Should be displaced. Why? By which the plate should be displaced in order to compensate the reduction in mass flux. The reduction in mass flux inside boundary layer. Inside boundary layer. That is again represented by the formula delta star is equal to integral 0 to delta 1 minus u upon u infinity times dy. This is the formula we are having. Okay, you can take this snapshot quickly. Yes, both the formulas are going to give you the same velocity, same answer. Both the ideas of the displacement thickness are going to give you the same answer. The plate should be displaced down now. If mass flux is moving up, the plate should be displaced down for mass flux to move at its actual level. Chali, let us see the application of this thing by taking a question, examination type question. Let us take a 2-mark question I'm going to take. Look at the slide, please. Imagine you're having a wind tunnel. Imagine you're having some wind tunnel. This wind tunnel is something like this. One second. Look over here. This over here is a side view of the wind tunnel. Side view. And this over here is a front view. Front view of the wind tunnel. There is some wind blowing into this thing. The cross section over here is circular. Let us say the diameter of this thing, the diameter over here is equal to some 100 mm. Diameter is equal to 100 mm. There is some flow taking place over here. Now we know by the concept of what you call development of flow that initially there is going to be some boundary layer formation taking place. Initially, some boundary layer formation is taking place. So let us say there is certain boundary layer formation. One second. There is certain boundary layer formation taking place over here. The boundary layer formation is something like this. You are having some boundary layer formation taking place over here. You are having some boundary layer formation taking place over here. Later on, these boundary layers are going to merge. So right now I'm having over here ideal flow, over here actual flow, actual flow. Let us say the input velocity over here, was initially equal to some 15 meters per second. Let us say this is u infinity 1 equal to 15 meters per second. Okay. I'm taking a particular section. Let us say I'm taking a particular section. Suppose this section over here is some section 2. This is some section 2. Over here, the velocity u infinity 2 is equal to how much is being asked. It is equal to how much is being asked. The value of delta over here is equal to 40 mm, and the value of delta over here is equal to 40 mm. It is equal to 40 mm. I hope you are following this. Boundary layer is going to have certain thickness, no? The thickness over here, this thickness over here is equal to how much? 40 mm. Similarly, the thickness over here is equal to 40 mm. I want to know how much is the u infinity value over here. How much is the u infinity value over here? I want to know. It is given to me. Given data over here, diameter is given to me. Initial velocity is 15 meters per second given to me. Okay, and delta values are given to me. Also given to me, u upon u infinity is equal to y by delta whole power 1 by 3. This is the velocity profile. U infinity 2 is equal to how much? This question is worth 2 marks in examination. Easily worth 2 marks question in examination. And let me tell you, this can be regarded as a difficult question in examination. It is regarded as a difficult question in examination. Not everyone would do this question. Let me write this cleanly. You concentrate, how am I doing this thing? You will understand everything. U infinity 1 is equal to 15 meters per second. U infinity 2 is equal to how much? Okay. You see, initially everywhere the velocity is going to be at section 1. Let us say this section 1, that is entrance section. Over there, the velocity throughout is going to be uniform. If the velocity throughout is uniform, later on over here velocities are 0, something more than 0, something more than 0, then attaining maximum. So for sure, when you enter into a pipe, your u infinity value should keep on increasing. U infinity value should keep on increasing as you enter into the pipe. U infinity value should keep on increasing. I am asking at this particular section, how much is the value of u infinity equal to? This is a question I'm having. Okay. How to solve this question? Solution now. Solution. Look over here. One second. One moment, please. Let us say this is a pipe we are having. This is a pipe we are having. And the boundary layer formation is something like this. You are having a boundary layer formation, something like this. If this is a boundary layer formation, then according to the second understanding means this understanding, according to this particular understanding, I can say inside the boundary layer, some portion I can assume is having no flow region. So if I assume there is no flow region in some portion, let us say some portion is having no flow region. Some portion is having no flow region. So let us say in this portion, there is no flow taking place. There is no flow taking place. Rest of the portion will have what kind of velocity profile? It should have a uniform velocity profile. So rest of the portion over here, let us say this portion over here is supposed to have what kind of velocity profile? It is supposed to have uniform velocity profile. Since it is section 2, the velocity over here is u infinity 2, u infinity 2. And the distance for which there is no flow, I'm imagining no flow over here. No flow. I'm imagining no flow over here. The distance for which there is no flow, the distance over here is going to be delta star. The distance is going to be delta star. Okay. So now what is happening? If I look at its image in the side view, its image in the side view is going to be a circle. My circle will not be as neat now. its image in the side view is going to be a circle. In this circle, some portion at the boundary, I'm imagining, is a no flow region. Some portion at the boundary, I'm imagining, is a no flow region. This over here is basically representing my no flow region. So now I'm having a diameter which is less. This diameter over here has to be equal to how much? It has to be d minus 2 times delta star. This is a diameter. So now I can use over here continuity equation. I can use continuity equation. I can say this is a1 and it is having a velocity u infinity 1. This is a2 and having a velocity u infinity 2. So I can say this is section 1, let us say. This is section 1. This over here is section 2. I can say by continuity equation a1 u infinity 1 has to be equal to a2 u infinity. A1 u infinity 1 has to be equal to A2 u infinity 2. What is the A1 value over here? A1 value over here is pi by 4 d1 square multiplied to u infinity 1 over here is equal to 15, has to be equal to A2 is equal to pi by 4. Diameter over here is equal to how much? D1 minus 2 times delta star whole square multiplied to what? U infinity 2. U infinity 2. How to get the value of delta star? You know very well that in this particular case, the value of delta star has to be equal to delta by 4. कैसे मालूम हमको ये? How do we know this thing? Because it's 1 by nth form. I told you in 1 by nth form, the value of delta star upon delta is 1 by n plus 1. I hope you are following all these things. Now put in the value of delta star is equal to delta by 4. From there, you get me the answer of what is u infinity 2 supposed to be equal to. Please start. Chali, get me the value of u infinity 2 from here. (23.43 meters per second). Is this understanding clear to all of you? Whenever a fluid is entering into a particular pipe, its centerline velocity keeps on increasing initially. See, U2 in reality is not uniform. U2 in reality is not uniform. If you want to understand how U2 is, let me create a duplicate slide. If you want to understand how U2 is actually, okay, those who are having a doubt, please look over here. U2 is going to be uniform only in this particular portion. U2 is going to be uniform in this particular portion. And over here, it is supposed to increase from 0 till here, 0 till here. It is going to be something like this. This is how U2 in reality is going to be. 1 second. This is how the velocity profile in reality is going to be. Because we know that when boundary layer formation has taken place, at the wall zero velocity till the boundary layer end, you are going to have variation velocity. Then in center, I'm having ideal flow. So over here, the velocity profile has to be uniform, again like this. Now look over here, I am basically saying that this much portion of flow, you think that it is not taking place. And I'm compensating by saying that it is taking place over here in the form of a uniform flow. Okay. I hope you are following what I have done over here. this much flow, okay, in no flow region, I'm thinking flow is not taking place. I am compensating it where? I'm compensating it over here. So look at this particular slide. Immediately look at this slide. What have I done? Immediately look at this slide. What have I done? I'm saying from here itself, let us start with uniform velocity profile, and below that, let us say there is no flow taking place. That particular height is known as your delta star. If it is still not clear to you, please go through this recorded video again. I know these topics will be slightly difficult if you're looking for the first time. Using the first approach, can you solve this? Yes, you can solve this. Delta by 4, see, I gave this particular velocity profile. For this velocity profile, n is equal to how much? 3. If n is equal to 3, look over here. Look over here. If n is equal to 3, the value of delta star has to be equal to delta divided by 3 plus 1. No? That way it is. This is given data in the question. All these are given data. He will give you velocity profile. This is given data. This is given data. You are supposed to find this out. So let us move further now. This was regarding the concept of displacement thickness. The next concept we are having over here. This result is useful in the concept of development of flow. If you know these things, then only you can talk about how the velocity at the center is keeping on increasing and what is going to be the maximum velocity at the center. You will come to know in development of flow, you will come to know by this particular method only. Without this method, you cannot study the concept of development or establishment of flow. Just imagine this slide itself is representing the concept of development of flow. These two boundary layers will meet at some particular point. They will converge over here sometime later on. So during the development of flow, how the velocity is keeping on changing, you can understand from here only. Apart from continuity equation, there is no other way you can solve it by. Actually, look over here now. We have spent a lot of time on this displacement thickness. There are two more thicknesses I have to talk about. The next thickness we have to talk about over here is known as momentum thickness. Momentum thickness. There's a particular thickness we have to speak about, which is known as momentum thickness, represented by theta. This momentum thickness is represented by theta. Now, how do we define this momentum thickness? How do we define this momentum thickness? See, this topic is, before I go any further, someone is mentioning that this is a bit bouncer topic, displacement thickness. It is, I don't know why you're feeling it that way, but I'll tell you, these are again very logical topics. These topics over here are extremely logical topics. It is all about compensation. Okay, this, let me do one thing. Let me again go in a very informal way to explain you some things. We understand physics better when we correlate it with real life. Okay, that is why mechanics seems to be a very natural topic. Okay, if someone says there is friction, it is easily acceptable. you will feel friction. A person who did not even study mechanics can understand what friction is. Let me do one thing. Don't type anything for some 5 minutes. Let me discuss entire today's class within 5 minutes, but in a casual way, in a very casual way. Okay. Everything over here is going by the word. Which word is it? Compensation. Compensation kya hai? Compensation basically means you are trying to, if there is some kind of reduction, if there is some kind of deficiency, you are trying to overcome the deficiency by giving somewhere extra. Okay. Let us say, let us say there is a particular pipe. There is a particular pipe. In this pipe, I gave over here. In this pipe, I gave over here some velocity. There are some 10 people who entered with this particular velocity. Some 10 people entered into this thing with some velocity. Okay. Let us say these people have entered with this velocity. Let us say 10 meters per second. How many people? Let us say 15 people have entered 10 meters per second. This person, after getting over here, he is saying, I am affected by no slip condition. I am not supposed to move forward. This person over here is saying, okay, fine, I will move forward with 1 meter per second. He's saying, okay, fine, 5 meters per second. Again, he's saying, okay, fine, I'll have over here 0 velocity. I'll have over here 1, I'll have over here 5. But whatever is the net effect of all these people should be the same over here. If you think like this, then what is happening? Ek jagah pe kam ho gaya. Over here, you have got reduction over here. So someone should compensate. So this middle people over here will take the burden of compensation. This middle people will take the burden of compensation. So what will happen? Their velocity will increase. They were entering with 10. Let us say they are going with 20 meters per second over here. This is how the center line velocity is going to keep on increasing. This is how the center line velocity keeps on increasing. Are you following? How does it further increase? Because as you even go further, even these particles will go into the boundary layer region. They will say, again, I have to reduce my velocity, they will say. So this center person keeps on increasing his velocity, keeps on increasing velocity to the point that the boundary layers will merge. Once the boundary layers merge, he will have a steady flow taking place. He'll have a steady flow taking place. Till that particular point when the boundary layers are not merging, his flow will not be steady. So actual velocity profile might be something like this. But for me to analyze this is very difficult. So what do I do? Again, you see, unless you do imagination, I cannot help you. How much ever I scream over here, I cannot help. And believe me, I'm screaming. I don't speak this loudly generally. Okay, we have a habit of speaking in mic, very low voice we speak with. But this is something which I'm screaming over here. Now, I cannot imagine. I find it difficult to analyze like this. तो मैं बोलता हूँ ठीक है काम करते हैं. These people are saying 1, 2, 3, 4, 5 velocity ना. Let us do one thing. Let us imagining they are not moving at all. इनको रोक ही दो. इतना ही मत करो आप. Let us make them. Let us think that they are not moving at all. And let us imagine again compensation. Let us imagine that when these people are not moving, their motion is being compensated by these people, such that throughout uniform velocity profile. Actually, it was supposed to be like this, but I'm saying these people are not moving at all. They are moving with uniform velocity profile. What is this height? I'm assuming they are not moving at all. Imagining not moving at all. इस height को हम बोलेंगे delta star. इस height को हम बोलेंगे delta star. Now look at this particular slide. What is it? Same thing. When I say people, you understand. When I say fluid, you don't understand. Why is it so? Actually, the fluid particles are moving like this. But I don't want to imagine this kind of motion. I want to say, I want to think that let us say these people are not moving at all. Let us compensate their motion over here. Let us imagine that this is moving with uniform velocity throughout. अब वो velocity जाहिर सी बात है बढ़ के रहना यहाँ से. Are you following? If I was having 15 over here, for sure this should be greater than 15. First thing you find out how much distance should I assume there is no motion. Usko delta star बोल लीजिए. Then after that you imagine how much is the cross section area over here that is equal to the cross section area of this inner circle. Then you say initially I was having this big cross section, over there I was having 15 velocity, later I'm having this small cross section, over there I'm having more velocity. How much is that more velocity? What is difficult in this? Are you following now? Is it clear now? Okay, now you got it. Very good. See, you people, you people want some kind of realistic images, but you have to create. देखिए, something there is. I'm not telling you what I'm telling right now is not just for my GATE class over here or my IES class over here. I'm telling you something for life. Remember this thing. Whenever you study, there is something called as concept, which is whose headache? Teacher's headache. There is something called as insight. This should be student's headache. If insight also is given by teacher, then somewhere the teacher is spoiling the student. This is something which I personally feel. Insight आप develop करना चाहिए, तब you will enjoy the subject. This was insight. I want you to develop. See, I can tell you many more things, but if you are not developing the insight, then somewhere I am, depriving you of the pleasure of this subject. आपको जो सब्जेक्ट का मजा है, वो मजा मैं आपको आने नहीं दे रहा हूँ. ओके, आप खुद कुछ चीजें पता करके एकदम अचानक से you will feel some kind of astonishment. Now, that astonishment should be with you, that you are losing. If I give you everything, some things you should develop. इसको imagine करना कैसे? I try to imagine like this. There are many ways I imagine. Okay, if I keep telling you, then lot of time will be taken. एक सेमेस्टर रहता, सेमेस्टर 6 महीने का रहता, 6 months semester will be there. कितना पढ़ते आप? 5.5 months you won't study at all. बाकी टाइम क्या करते? कंपेंसेशन करते. कैसे पढ़ते? कैसे पढ़ते? You won't sleep at all. That is how you study. That is what happens. A semester is supposed to be studied something like this. Every day, small amount of study you have to do. But what do? You don't study at all. For a major part of the portion, you don't study at all. Then how do you study? Like this you study. इतना लंबा लंबा पढ़ते तो थोड़े दिन के अंदर. Because you have to compensate. Is it not? All these things you should develop. कैसे subject के अंदर कैसे correlation create करना, all these things should develop. Everything if I keep saying, then you will lose the pleasure of the subject. Okay. Chaliye, let us now move further. A lot of discussion has happened now. I hope all these things are clear to you now. Okay. There are many more things I would want to say, but right now let us go from examination point of view. Chaliye. But please develop this particular habit, especially if you're going to do your MTech masters or something. Try to take interest in the subject. Okay. As long as you study from examination point of view, as long as you study from getting marks point of view, you will lose interest. और आपको मजा नहीं आता, वो life बेकार है. That much time you are wasting. But when you start enjoying subject, now that is something which is interesting. चलो चलो बहुत हो गया time pass. Let us say momentum thickness. Momentum thickness theta. Momentum thickness theta. देखिए, mass flux got reduced. If mass flux is getting reduced, automatically momentum flux also has to get reduced. If momentum flux is getting reduced, there has to be some amount of distance perpendicular to the plate, which should be, again, same story. Some distance perpendicular to the plate by which the plate should be displaced, so that I'm having some momentum flux compensation taking place. जैसे mass flux compensation was done, similarly momentum flux compensation is being done over here. So straight away I can write the distance measured perpendicular to surface by which the plate should be displaced in order to compensate the reduction in momentum flux inside the boundary layer. Inside the boundary layer, momentum flux is going to get reduced. In order to compensate the reduction in momentum flux, the distance measured perpendicular to the plate by which you are displacing the plate is known as momentum thickness. Now, regarding this momentum thickness, the value of theta, very important formula. Theta is equal to how much? Integral 0 to delta u upon u infinity multiplied to 1 minus u upon u infinity multiplied to dy. This is a formula for momentum thickness. This is a formula for momentum thickness. Okay. Now, regarding momentum thickness, there are some points you are supposed to remember. पहले तो इसको mark कर लीजिए. This formula you have to memorize. You have to memorize this particular formula. Now, regarding momentum thickness, first thing you remember, the value of theta is always less than delta star. Delta star was displacement thickness, theta is momentum thickness. Okay, theta will be always less than delta star. Okay. Why is it less than delta star? Just imagine for a moment that if I remove this part off, then what is it representing? It is representing delta star. If I remove that part, just now I removed now, if I remove that part off, it is representing delta star. Now I am actually multiplying this part to delta star. I am multiplying this part to delta star, which is always less than 1. U by infinity dekhiye, it is always less than 1. So therefore delta star is being multiplied to something which is less than 1. Automatically theta will be less than delta star. Theta will be less than delta star. Next thing, the value of delta star upon theta is given by h. This is known as shape factor. Someone was asking me a doubt yesterday, what is shape factor? It is a ratio of which two thicknesses? Displacement thickness to momentum thickness. अब एक और बात बोल सकते हैं आप, क्या बोल सकते हैं? H should always be greater than 1 बोल सकते हैं, क्योंकि delta star is greater than theta, तो H should always be greater than 1. Third point, very important point. From here, 2-mark question we are going to do now. Okay, very important point. This point says that in a 2D steady incompressible boundary layer with dp upon dx equal to 0, the relationship between tau naught and theta is given by something known as Kármán momentum integral equation. Kármán momentum integral equation. Very important equation. This yesterday I told you that the heart of this particular topic can be an equation called as Kármán momentum integral equation. That is what I'm mentioning over here. The relationship between tau naught, wall shear stress, and momentum thickness is given by Kármán momentum integral equation. This is important. From here, questions have appeared in examination. The equation goes something like this: tau naught upon rho u infinity square is equal to dou theta by dou x. This is the equation. Take a snapshot of this thing. We are going to solve a question on this thing using this concept. A 2-mark question in GATE examination. We are going to solve. Chaliye. Take a snapshot quickly. And in your rough book, whichever you are following my writing some things right now, mention this formula, mention this particular formula. We are going to take up a question now. Chaliye. 1 second. Yes, quickly take down the formulas. चलिए, now imagine the question is like this. Plate, there is a plate, width is equal to 3 meters, width क्या है, b is equal to 3 meters, length not given. This is important. Whenever questions like this come, length not given, length not given. Okay, a plate is there, width is equal to 3 meters, length is not given in the question. ऐसे नहीं बोलेगा length is not given. Okay, you have to read the question and you have to understand length is not given over there. It says that the value of u infinity is equal to 20 meters per second. Air is flowing over there. Density is equal to 1.25 kg per meter cube. Boundary layer thickness u upon u infinity is equal to y. Velocity profile is equal to y by delta. The value of delta at trailing edge is equal to some 15 mm. Delta at trailing edge is equal to some 15 mm. All this much is mentioned. He's asking you, find the drag force if boundary layer formation takes place on both sides, of the plate. Find the drag force if boundary layer formation takes place on both sides of the plate. Okay, आप imagine कीजिए एक plate है. Okay, this is a plate, let us say. Fine, 1 second. This is a plate, let us say. Over here also boundary layer formation, over here also boundary layer formation. The value of b is given to you. This is b is given to you, but the value of length is not given to you. This is L, it is not given to you. Over here height is given to you, boundary layer thickness is given to you. Okay, chaliye. Now how to solve this question? How do we solve this question? You draw a diagram first of all. एक rough diagram draw कर लीजिए. You are having some boundary layer formation here and here. There is going to be drag here, there is going to be drag here. On either sides you are going to have drag. This distance is given to you as how much? 15 mm. The free stream is equal to u infinity is equal to कितना है? 20 meters per second. 20 meters per second. Again same thing, same story, 15 mm over here also. Chaliye, how do you have to find out drag force? Recall from yesterday's class, the value of FD was having two formulas. Two formulas were there for FD. One formula we were having was B into integral tau naught times dx ranging from 0 to L. This is x is equal to 0. This is x is equal to L. But this would be wrong over here. Why would it be wrong? Please be careful. It has to be 2b over here. Why should it be 2b? Because right now drag is excuse me. Right now drag is taking place on both the sides of the plate. Boundary layer is on both the sides, therefore you have to multiply by 2. This should be the formula. Okay, one more formula is coefficient of drag into area multiplied to half rho u infinity square. But right now we do not know the value of coefficient of drag over here. We do not know the value of coefficient of drag. So this formula we are going to use. This is the formula. Yesterday we have seen this particular formula. We are going to use this formula. But there is one more problem. Look carefully. Do I know the value of L? That is why I underline this. Anytime the question comes on drag force where length is not given, you will be trapped. The only exit over here, the only way out over here is to use Kármán momentum integral equation. Why? Now what to do? Since I'm trapped over here, I have to think of eliminating this entire integral. 2b I know. 2b is equal to some 2 times 3. Fine, I know that thing. I want to eliminate this entire integral over here. ये integral को eliminate करना चाह रहा हूं मैं. How do I eliminate this entire integral? Think of tau naught and dx. Look over here. Tau naught and dx over here are present. ठीक है? If they are present, let me do one thing. let me say now that by momentum integral equation, tau naught upon rho into u infinity square is equal to d theta by dx. It is a 1D flow, therefore I'm writing d theta by dx, which implies tau naught times dx is equal to rho u infinity square into d theta. Rho u infinity square into d theta. Okay. Now, before applying integral, let me find out the value of theta. Let me find the value of theta. Okay, how do I find the value of theta? Theta is equal to integral 0 to delta u upon u infinity multiplied to 1 minus u upon u infinity times dy. This is a formula we are having. If you put in that u upon u infinity is equal to y by delta, so this is equal to integral 0 to delta y by delta into 1 minus y by delta into dy. If you do this entire integration, okay, very simple integration, if you do this entire integration, you will get the value of theta is equal to delta divided by 6. If you do this integration, very simple integration, you will get the value of theta is equal to delta divided by 6. If theta is equal to delta divided by 6 implies d theta is equal to d delta divided by 6. D theta is equal to d delta divided by 6. Okay, fine. Once I have this particular thing, अब मैं क्या करूंगा? In this particular equation, in place of d theta, I am going to put d delta by 6. Okay. I hope all of you have done along with me till here. If you are not done, I'll give you a moment. You do it. Those who have done, please go further. d theta को replace कीजिए d delta by 6 के साथ. Replace d theta by d delta by 6. Momentum flux is equal to mass flux multiplied to velocity. So rho a into v square. चलिए. Now I'm having over here tau naught into dx has to be equal to rho u infinity square into d delta divided by 6. This is what I'm having. Now I'm looking for the integral. I'm looking for the integral. At x is equal to 0, I know delta has to be equal to 0. At x is equal to L. I don't know the value of L, but I know the value of delta over here is 15 mm. I know it is given to me in the question. The value of delta over here is equal to how much? 15 mm is the value of delta I'm having. Okay. If you do the integration, don't worry. If you do this particular integration, you will get this particular value. I'm straight away taking the value. Okay. You can do the integration later on. Now, अब मैं क्या करूंगा? In this particular equation, that is, if f was equal to 2 times b integral tau naught times dx from 0 to L, I am now going to write down. In place of this thing, I'll write this thing. So 2 times b rho u infinity square integral d delta by 6 ranging from 0 to 15 mm. Take everything in SI units, get me the answer. Please be quick. Everything in SI units, get me the answer. Do the calculation. $7.5 I'll take. Sai Krishna and Amit Anil. Okay, many people are giving the same answer. I'll take the answer as 7.5 Newton then. Okay. This kind of question has appeared for 2 marks in GATE examination. Many interesting questions are there. This topic actually is a very interesting topic. If you try to create some correlations, you will see that this topic becomes very interesting. This was regarding the concept of momentum thickness along with the problem. Okay. So the net drag force we are having is equal to 7.5 newtons on this particular plate. Please understand when to use this particular technique whenever length is not given. You will see all this in the previous gate questions. If you go through previous gate, you will see these things. Chaliye. I'm moving further now. The next topic I'm taking down is known as energy thickness. We did not take L is equal to 15 mm. We said at X is equal to L, delta is equal to 15 mm. We are putting the corresponding limits over here. Delta was given to me in the question. Delta at trailing edge is equal to 15 mm was given to me in the question. Okay. So trailing edge position is not given to me, but trailing edge delta is given to me. So when we are integrating, we should put corresponding limits over here. That is what I'm doing. Chaliye. Now the next topic we are having, last topic in thickness is energy thickness. Energy thickness. This energy thickness is given by delta double star, or some books also use delta E for energy thickness. Some books use delta E for energy thickness. Okay. Now, how do we define energy thickness? Same concept. Whatever we have discussed previously for momentum thickness, same thing. देखिए, mass flux is getting reduced, momentum flux is getting reduced, even energy flux will get reduced. To compensate, what we are doing, we are pushing down the plate. We are pushing down the plate. The corresponding distances are known as displacement thickness, momentum thickness, and energy thickness. So this over here is the distance measured, the distance measured perpendicular to the plate by which the plate should be displaced. The plate should be displaced in order to compensate the reduction in energy flux taking place inside boundary layer. देखिए inside boundary layer all these things are happening because inside boundary layer viscous forces are acting. If viscous forces act, they will try to reduce the flow, that is mass flux. Mass flux means m dot, that is m dot is equal to how much? M dot is equal to how much? Rho av. देखिए velocity's reduction is causing reduction in mass flux. Then if mass flux gets reduced, then momentum flux also should get reduced, because momentum flux is based on mass flux, and energy flux is half m dot into v square. If velocity is reducing, mass flux will reduce, momentum flux will reduce, energy flux will also reduce. All these things are getting reduced. For this, we are having a compensating distance called as displacement thickness. For him, I'm having something known as momentum thickness. For him, I'm having something known as energy thickness. Okay, I hope it is clear now. What is the formula? You have to memorize the formula over here. Delta double star has to be equal to integral 0 to delta u upon u infinity into 1 minus u upon u infinity square times dy. This is the formula we are having. Okay. One more thing I want you to memorize. Better memorize this thing. In examination, I told you many times linear velocity profile is coming. Therefore, remember some standard results for linear velocity profile. Standard results, yaad rakhiye aap. Okay, what are the standard results? For linear velocity profile, the value of delta star we know is equal to delta by 2. The value of theta is equal to delta by 6. Remember this thing. And the value of delta double star, that is energy thickness, has to be delta by 4. Shape factor has to be equal to delta star by theta. It should be equal to 3. Remember all these things. For which velocity profile? For linear velocity profile. This is for linear velocity profile. Take down this snapshot. Excuse me. Chaliye. With this, we complete the concept of thicknesses. Now, very small topic is left in boundary layer theory. Okay. This concept is known as boundary layer separation. This concept is known as boundary layer separation. This is known as boundary layer separation. One second. Those who want the previous slide can take down very quickly. Chलिए. In every case, we are pushing the plate against the direction of delta. We are pushing the plate against the direction of delta. H is shape factor. H over here is shape factor. H is shape factor. Shape factor याद है आपको? H is shape factor. Questions come in examination on shape factor also. Okay. चलिए boundary layer separation देखते हैं. All of you remember there is something called as adverse pressure gradient. याद कीजिए concept which we discussed previously in minor losses. There is something known as adverse pressure gradient. Adverse pressure gradient means when the value of dP upon dx is positive. Remember, whenever the value of dP upon dx is positive, the fluid is going to experience retardation. Okay, chaliye, look over here. Adverse pressure gradient. जल्दी recall करेंगे इसको. Pressure gradient. This basically means dP upon dx is equal to positive. If dP upon dx is equal to positive, what will happen? Flow retards. Flow is going to experience negative acceleration or retardation. Velocity keeps on reducing. देखिए, pressure increases, so velocity has to reduce. Flow is experiencing retardation. To the point that we have also discussed, there is going to be some reversal of flow taking place. Reversal of flow is going to take place. It is going to cause something known as eddies. All these things we have discussed. Okay. We are going to apply this concept in the case of boundary layer now. Imagine that you are having some surface like this. You are having some surface like this. Some surface you are having like this. And over here, you are allowing some fluid to flow. You are allowing some fluid to flow over here. Let us say the fluid is flowing over here with certain velocity u infinity. Now, as the fluid flows forward, please observe, from here to here, what is happening? The cross-section area of flow is decreasing. Okay, you write down in the side of your paper, you write down area decreasing. If area is decreasing over here, velocity is increasing. Accelerated flow hai. That means as you keep moving forward, pressure is decreasing. So in this particular region, pressure is decreasing. Therefore, over here, dP upon dx is over here going to be negative. Negative means what kind of pressure gradient? याद कीजिए, it is going to be favorable pressure gradient. Now you see from here forward, if you see downstream over here, over there area is increasing. If area increases, continuity equation says velocity decreases, retarded flow. What is going to happen? Pressure is increasing. That means dP upon dx is going to be positive, which is non-favorable or adverse case. Now what will happen over here? When the fluid is moving in this particular portion, in this dP upon dx is negative, anywhere if you see, you're going to have some velocity profile developed, boundary layer is going to be there. Everything till here is fine. Everything is good. But the moment you are going to cross this particular point, the moment you are crossing this particular point, we know that there has to be some region of reversal of flow taking place. Eddies are going to be formed over here. Some reversal of flow is going to take place over here. If there is going to be some reversal taking place over here, there is some reversal of flow taking place over here at any section, let us say there is some region of reversal of flow. At any section, if I look at the velocity profile, I'm supposed to have a reversed velocity profile first, and then a forward velocity profile. Why reversal of flow? Reversal of flow, I told you over here, adverse pressure gradient, reversal of flow, eddies are going to be there. This region of reversal of flow is known as wake. It is known as wake. So what has happened now? The flow wanted to move forward, but the pressure forces are pushing back the flow. Imagine over here, pressure forces at the next section. Dekhiye, if you take a particular control volume, over here, let us say you are having P1, over here you are having P2, this is some distance X. We know as I move forward, P2 is going to be greater. If P2 is going to be greater, then what is happening? This fluid, this element is getting a smaller push over here. He is getting a bigger push over here. That's why the element is getting reversed over here. So the reversal of flow takes place. Because of this reversal of flow, look at what has happened to boundary layer. It was sticking to the surface previously. The boundary layer was always sticking to the surface. Dekhiye, this was boundary layer. It was sticking to the surface. Now the boundary layer is getting separated from the surface. The boundary layer separates from the surface. It was previously sticking to the surface. Ab wo surface se ud gaya. It is getting separated from the surface. This tendency is known as your boundary layer separation. For boundary layer separation to take place, the concept is the value of dP upon dx has to be what? Positive. Whenever dP upon dx is positive, boundary layer separation takes place. Now look at this thing. Look at the tangent over here. Look at the tangent over here. If I draw a tangent to the velocity profile, the tangent is something like this. The tangent is something like this. If I say this is my y-axis, perpendicular axis over here is y-axis, I can say the value of dou u upon dou y at y equal to 0, it is positive. It is positive. Now look at the tangent over here. Look at the tangent over here. I can say the value of dou u upon dou y at y equal to 0. What is happening now? Tangent is in the reverse direction. So yeah, I'm having a negative slope. Therefore, this value over here is negative. Now your velocity gradient at y equal to 0 is shifting from positive to negative. So somewhere in between at a particular point, the velocity gradient should also be equal to 0. Positive and negative बन रहा, हल्लो look धीरे धीरे कम हो रहा वो. If it is going to keep on reducing slowly, then at a particular point, there has to be a 0 value of du by dy also. That is what you're going to get over here. Let us say at a particular section, if you look at the velocity profile, the velocity profile is going to be like this. This over here, this over here is known as your point of separation. At the point of separation, dou u by dou y at y equal to 0 has to be equal to 0. At which point? At the point of separation. I hope you are following all these things. Summary. I'm going to write down everything in summary over here. In every surface, you are going to have boundary layer separation created. Now, regarding hydraulic jump, I'm sorry, I do not have an idea regarding that. You can ask your open channel faculty. He will tell you better regarding hydraulic jump. Okay, chali. Now, moving further, one second. Let me summarize. If you want, you can take a snapshot of this particular slide. Let me erase this part. You can take a snapshot of this thing. In every flow, boundary layer takes place. Only boundary layer does not take place in the case of ideal flow. If a flow is real, boundary layer should take place. Excuse me. Now I'm writing the summary of entire thing. When a boundary layer encounters adverse pressure gradient, when a boundary layer encounters adverse pressure gradient, what is the meaning of adverse pressure gradient? dP upon dx is positive. Now what happens whenever boundary layer comes across this adverse pressure gradient? A region of reversal of flow. A region of reversal of flow known as wake is formed. This causes boundary layer to separate from the surface. This causes boundary layer to separate from the surface. This is known as boundary layer separation. This is known as boundary layer separation. It is known as boundary layer separation. So whenever you are having adverse pressure gradient, you are going to have a region called as wake formed. Wake is basically the zone of reversal. Wake क्या है? The zone of reversal, the region of reversal of flow is known as wake. Now, because of formation of wake, what is happening? The boundary layer is no more attached to the surface. It is getting displaced up. It was initially up touching, then because of reversal of flow, it has moved up. This region in between is the wake region. Boundary layer has got separated now. This is known as boundary layer separation. As a matter of fact, boundary layer separation is experienced whenever you have positive pressure gradient. Okay. Now, is this boundary layer separation favorable? Mostly it is not favorable. Why is it not favorable? It is not favorable because it is going to lead to losses. You see, reversal of flow is going to create eddy losses. Okay. Boundary layer separation is not favorable since it leads to eddy losses. Since it is leading to eddy losses. So somehow you have to overcome the boundary layer separation. Generally, many books write down that we avoid boundary layer separation by doing these things. Remember one thing, you cannot completely avoid boundary layer separation. It is not possible. Completely avoiding boundary layer separation is not possible. You can reduce boundary layer separation. Okay. So therefore, boundary layer separation has to be reduced. Therefore, boundary layer separation has to be reduced. How to reduce boundary layer separation? There are many methods. Okay, I'll tell you about two methods particularly. There, after that, I'll show you some three methods diagrams. First two methods. Reduction of bond layer separation is done by first method, that is streamlining a body. Streamlining a body. Streamlined body basically means a body in which the streamlines can flow very smoothly over its surface. That is called a streamlined body. The opposite of streamlined body is called as a bluff body. We will see in the next chapter. Okay, streamlined body is something which will allow the streamlines to move very smoothly over its surface. Imagine I'm having a fish. Let us say there is a fish over here. So the streamlines are going to move very smoothly over its surface. So fish generally is a streamlined body. Okay, but what about a plate perpendicular to the flow? Imagine a plate is there perpendicular to flow. If a plate is there perpendicular to flow, it is not a streamlined body. It is not allowing the streamlines to flow smoothly over its surface. Such a body is called as bluff body. One way of reducing boundary layer separation is by making the body more and more streamlined. I'll give you an example which is very easily imaginable. You take any vehicle, any common car on road, and imagine its models from the past 15 years up till now. Okay, one of the simplest example you can take, which is a very common car on roads, is Honda City. Honda City is quite common. Okay, Honda City some 15 years, 20 years back. Okay, I remember it used to have a kind of model which was more like a box piece. Okay, dabba tha pehle. Then what happened over a period of time? If you see the latest models nowadays, okay, some people call it as a dolphin nose model. You're having a model which is very sleek. Now what have you done over here? You have made the body more and more streamlined. Okay, what advantage are you having in this particular model? In this Honda City model, which is an older model, you are having a lot of boundary layer separations taking place. When a body wanted to move forward, it was having a lot of separation taking place. Therefore, it was experiencing a lot of losses. Mileage kam ho jayega. Okay, you are going to get lesser fuel efficiency. But if you make the model more and more, I can't draw a better diagram. Okay, you imagine the diagram. If you make the model more and more sleek, then what is happening? The body has become more streamlined. The boundary layer separations reduce. Boundary layer separations reduce. Once the boundary layer separations are going to get reduced, automatically the fuel efficiency is going to get increased. So one method, the most important method, is streamlining of a particular body. Second method, second method is using rough surfaces. Now this might seem strange to you. Using rough surface also reduces boundary layer separation. Okay, using rough surfaces also reduces boundary layer separation. I'll give you an example which you can relate to very easily. Okay, you might have seen, if you watch test cricket, first of all, I do not encourage watching test cricket. It wastes lots of time. But if you ever watch test cricket, then you know that initially when a ball is a new ball, that time generally fast bowlers take up that ball. Imagine that this is a ball you're having, this is a seam position you have. The surface over here is perfectly smooth. You're having a very smooth surface. As the ball is traveling forward, as the ball is traveling forward, you're going to have smooth surface. Separation will take place very quickly. You're going to have lot of wake formation over here. Now, same ball, let us say an older ball is taken. Let us say some 50 overs old ball is taken. Same bowler is taking. Now what happens? The ball becomes rough. Let us say the ball has become rough. If the ball becomes rough over here, because of roughening of the ball, boundary layer separation is going to become lesser. It is going to get reduced because a rough surface has more capacity to hold on to boundary layer. It holds on to boundary layer better. Okay, so now what happens? The separation is going to take place much later. Let us say you're having this much region of wake, this much region of, initially you're having more region of wake, later you're having less region of wake. Automatically the speed is going to get increased. Same bowler, same arm power he's using, but initially the speed will be less, later on the speed is going to be more. Okay, this concept was used in early 1980s to develop the concept of reverse swing. Okay, a very simple and oversimplified concept of reverse swing is something like this. Imagine you are having a ball which was completely smooth, it was having this kind of wake formation. Completely rough, it is having this kind of wake formation. So a particular bowler by the name Sarfaraz Nawaz, he thought of this idea first. He thought that let us make one side of the ball rough, or let us allow one side of the ball rough. Why did I use the word allow? Because if you make one side of the ball rough, it becomes tampering, right? If you allow it to become rough, it is fine. But every year you're seeing many cases, right? They deliberately make the one side of the ball rough. That is tampering. That is not allowed. It is beyond the spirit of the game. Okay. So let us say they allow one side of the ball to become rough, and they keep on doing some, some antics on the ground to make one side smooth. You might have seen one person always rubbing that ball one side on his trouser. His trouser is never white. He keeps rubbing, keeps rubbing. So what happens? One side becomes smooth. Fine. So you allowed one side to become rough. The other side is smooth. If this rough side is there, it is going to experience separation later. Smooth side is going to experience separation early. You are having an imbalanced wake, the ball will swing now. The ball will swing. This is basically an oversimplified idea of a reverse swing in a particular ball. Fine. Yeah, I watch a lot of cricket. I really like cricket, but these days I don't watch cricket. I like test cricket a lot. Fine. So these days it is more of a entertainment factor than good cricket. Anyway, so this is regarding the concept of using rough surfaces. Fine. Yeah, Steve Smith is the latest feature in the list of tampering thing, though I like him a lot. Chali, this is regarding some methods of reducing boundary layer separation. Apart from these methods, one second. Apart from these methods, I'm showing a diagram over here. These are some other methods of reducing boundary layer separation. Okay, these are secondary methods which are mostly used in the case of aerofoils. We'll discuss aerofoils later on. Okay, this is injecting a fluid into the boundary. Now imagine over here, you are having, one second, let me create duplicate slide. This 15F slide I'm saving for you to refer anytime. In 16F, I'm going to explain this thing. You see, the fluid was trying to get separated over here. The fluid was trying to get separated, boundary layer was getting separated over here. In this region, there was a reversal of flow taking place. But what you have done, you are injecting some fluid by using some mechanism, you are injecting the fluid over here. So what happens? The fluid is again going to move forward in this particular region. So this method is called as injecting the fluid into boundary layer. An advanced method of injecting the fluid into boundary layer is this method, slotted wing. अब देखिए, you are not using some mechanism over here to inject the fluid. You are rather trying to lift the fluid, or you are trying to inject the fluid by creating a slot over here. When you create a slot over here, automatically from the streamline below, the fluid, some portion of the fluid is going to move like this. So that is an automatic. You are not yourself doing some injecting. You are allowing the fluid itself to inject over here. That is one more thing. Acha, ye hai suction. It is the opposite now. In suction case, what you're going to do, you're going to create a region where whatever is a reversed flow, instead of flow getting displaced or it is getting separated over here, it is trying to come down. So eventually it is getting compensated. Fine. These are, just remember the names at least. Injecting fluid, slotted wings, suction of fluid from boundary, rotating a body. You can have one more method. That method is, imagine a body is experiencing boundary layer separation. If you rotate the body, then the boundary layer separation is going to get reduced. Okay. So these are some methods. Rotating a body. That is also some methods. So this is regarding the concept of boundary layer separation. See, boundary layer formation itself is not favorable. Very good question. Swarangi Marathi has asked this question. Is boundary layer formation favorable? याद रखिए, boundary layer formation itself is not favorable.
but it will happen. In that, boundary layer separation is even more unfavorable. It is going to cause losses. Okay, formation itself is not favorable, separation is even more unfavorable for us. Why boundary layer formation is not favorable? It is reducing mass flux, momentum flux, all these things are happening. That is why it is not favorable. Okay, viscous effects are going to create losses. That is why it is not favorable. Okay, chaliye, this is regarding the concept of very good question. Someone is asking me regarding top spin. Has it to do anything with the rotation of body? Okay, someone seems to be a fan of tennis. Okay, top spin is actually a concept tomorrow we are going to see known as Magnus effect. There is something known as Magnus effect. Top spin belongs to that particular concept. Okay, in lawn tennis you might have seen something called as top spin. That is actually coming from Magnus effect. Similar kind of things happen in football also. There are some peculiar kind of kicks which belong to Magnus effect. When a rotating body is in a stream of flow, that time the body is going to experience some lift. That is known as Magnus effect. Okay. Shali. With this, one more thing I want to discuss over here is the concept of boundary conditions. Boundary conditions. We'll close the chapter with this topic, boundary conditions. Small 2 minutes topic only. Boundary conditions. The concept is something like this. Imagine you're having a surface. On this surface, you're having a boundary layer formation. A boundary layer formation. This, let us say, is y-axis. This, let us say, is y-axis. Okay. At y equal to 0 and at y equal to delta, we have to see. At y equal to 0, u is equal to 0, du upon dy is maximum, and d2u upon dy2 has to be equal to 0. Since du by dy is maximum, d2u by dy2 has to be equal to 0. Its differential has to be equal to 0. At y equal to delta, u is equal to, strictly speaking, 0.99 u infinity. Lekin we will make assumption. Small error we will deliberately do. That is, u is equal to u infinity. And the value of du upon dy is equal to 0. Du upon dy is equal to 0. And from here onward, shear stress also is 0. These are the boundary conditions when you're having boundary layer formation. When you're having boundary layer formation. The other condition you're having, imagine, at separation, at separation, imagine at the point of separation, let us say you have this kind of velocity profile. This is again y-axis. Again, I'm going to look at y equal to 0 and at y equal to delta. At y equal to 0, again u is equal to 0. At separation, even the value of du by dy is equal to 0. At separation, even the value of du by dy is equal to 0. Just now we have mentioned. At separation, the value of dou u by dou y at y equal to 0 is 0. Okay. At y equal delta, u is equal to u infinity. Again, the value of du by dy is going to be equal to 0. Remember these boundary conditions. Okay. You can take a snapshot of this particular slide. With this, we complete the chapter of boundary layer theory along with problems. Okay, we don't have much time to start the next chapter. I'll take up some of your questions if you have any. Yeah, tomorrow will be the last date for civil batch. Ganesh,
Hello, good morning, sir.
good morning. Tell me.
Sir, I had doubt that means they are deriving these formulas means theta, delta star, all these, but how they are validating these formulas means the streamlines functions and all these concepts are imaginary. So after getting that formula, the results are means okay, correct or what? How they are validating?
No, streamlines is not imaginary. Visualization of streamlines is imaginary. Or we can say basically a streamline is a very, you know, you cannot visualize streamlines actually.
That's why, sir, means they are means we are not able to visualize the streamlines.
That's
Then
right.
whatever the results they are getting. So on what basis they are getting these results? Means streamlines to locate the streamline is it is not possible.
But
But
you can still, if there is a particular velocity profile, we can still imagine the streamlines by the equation, right?
sir, but one streamline we will get, but adjacent to its means other streamline we don't know the location.
No, we
Means
can get an
infinite
entire
possibility.
family of streamlines. I have shown you a problem. Okay, for example, I gave you that velocity u is equal to x, the velocity v is equal to minus y. If you look at this thing, you're going to get a family of streamlines.
Okay.
But once you get a family of streamlines, let us say you're having a family of streamlines which are hyperbolic. You can say all these streamlines are a family of streamlines. Once you get a family of streamlines, then everything is fine. You can imagine any result. Okay,
Okay.
don't think that you have to work separately for every streamlines.
Okay. Okay. And
Okay.
sir, another doubt is there. Sir, that compensation problem means you still the means compensate this to the uniform variation you assume rectangle means parabolic conversion converted into rectangle
हाँ हाँ
area velocity means u infinity.
हाँ हाँ.
In that case, sir, means how do we come to know that whatever the delta they given at that delta whatever we are calculating it will be the maximum.
Can you come again?
सर मैं बोल
What
रहा
is
था कि
maximum?
मतलब
जी
डेल्टा जो दिया है उन्होंने क्वेश्चन पे
जी
क्वेश्चन
जी
में सो
जी.
वो डेल्टा के लिए जो यू मतलब यू का वेलोसिटी मतलब वेलोसिटी जो कैलकुलेट कर रहे हैं
हाँ,
वो मैक्सिमम हो रहा है जो कन्वर्जन करने के बाद भी वही वैल्यू आएगा वो कैसे पता चला मतलब वही पॉइंट पे
मैं मतलब
सर वो डायग्राम
कौन
सर
सा
आपने जो
ये
पैराबोलिक
डायग्राम?
कन्वर्जन किया था सर पैराबोलिक का रेक्टेंगुलर में कन्वर्ट किया
कौन सा ये
तो
डायग्राम बोल रहे हैं आप?
ये नहीं सर वो न्यूमेरिकल में
अच्छा, ये डायग्राम.
हाँ तो वो जो डेल्टा के वहां पे जो मतलब सेंटर वाला पार्ट है ना रेड लाइन वर्टिकल वाला कांस्टेंट वाला
हाँ हाँ हाँ
तो वो जो एक्स्ट्रा ऐड किया ना ऊपर
हाँ
के एक्स्ट्रा से
हाँ
तो
हाँ.
वही वैल्यू आएगा वो पॉइंट पे मतलब वो डेल्टा पे वो कैसे पता चले
वही तो डेफिनेशन है ना सर. अगर आपको चाहिए कि भाई यूनिफॉर्म वेलोसिटी प्रोफाइल रहे, तब आप डेल्टा स्टार ऊपर जा रहे हैं. आप बताइए, सेंटर लाइन की वेलोसिटी यू इन्फिनिटी रहेगी,
हाँ सर
तो यूनिफॉर्म के लिए हर किसी की वेलोसिटी यू इन्फिनिटी होनी चाहिए यहाँ पे.
हाँ सर बट जब डेल्टा आपका आएगा मतलब ये डेल्टा स्टार के लिए यू मैक्स अलग होगा और अगले पॉइंट पे यू मैक्स अलग ही होगा ना क्योंकि वो फिर
हाँ, अलग होगा. अगर
हाँ
इस पॉइंट पे अलग होगा, इस पॉइंट पे अलग होगा, हर पॉइंट पे अलग होगा.
हाँ
लेकिन उसने बोल दिया ना, उसने क्वेश्चन में बोल दिया कि भाई इस पॉइंट पे पता कीजिए, आप डेल्टा इक्वल टू 40 पे पता कीजिए आप.
तो फिर वो जो मतलब ऊपर के डायग्राम में जो डेल्टा इक्वल टू 40 के लिए हमने कंपनसेट किया ना इधर
हाँ
तो
हाँ.
मैं बोल रहा था कि ये कंपनसेट करने के बाद वो
हम्म.
जो हम कंपनसेट कर रहे हैं वो वही पॉइंट पे मतलब वो करेक्ट आएगा वो कैसे पता चला मतलब अगर मैं समझो वो
हम्म.
आपने यहाँ पे जो मतलब वर्टिकल इसमें कंपनसेट किया ना मतलब हाइट बढ़ा दिया और
हाँ,
अपना विड्थ सेम रह दिया मतलब यू इन्फिनिटी का वैल्यू
बढ़ा दिया.
हाँ तो वो वैल्यू पहले जो था वही रखा बट वर्टिकल में डिस्प्लेस किया
अच्छा 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 अच्छा. इस केस के अंदर हमने सेम वैल्यू रखा, इस केस के अंदर हमने सेम वैल्यू नहीं रखा.
नहीं सर वो नहीं बोल रहा यू इन्फिनिटी 2 का है ना
हाँ
यहाँ पे जो 2 सेक्शन पे जो वैल्यू था वो
हाँ
कांस्टेंट अज्यूम किया बट बराबर ना
हाँ
सर अगर
हाँ.
ये कंपनसेट नहीं करते तो यू इन्फिनिटी 2 एक वैल्यू है समझो
जी
15
जी.
वही 15 रख दिया बट वर्टिकल में डिस्प्लेस किया जो पैराबोलिक था उसको इसमें कन्वर्ट करके वो वैल्यू रख दिया बट वर्टिकल में एक्स्ट्रा बढ़ा दिया बराबर सर मतलब ये 2 सेक्शन पे जो हाइट था
इसमें हाइट नहीं है ना सर, इसमें तो
सर
क्रॉस
मतलब जो
सेक्शन.
भी उसका क्रॉस सेक्शन था ना सर
जी.
मतलब ओरिजिनली तो
हाँ
वहां पे बढ़ा दिया प्रीवियस से, बराबर।
एक काम करता हूँ, मैं आपको समझाता हूँ, उसके बाद आप डाउट पूछिए।
ओके।
देखिए यहाँ पे इस केस के अंदर आप एक्सपोज टू एटमॉस्फेयर है, इसीलिए
हाँ
आपका यूनिफिनिटी जितना था शुरू में उतना ही यूनिफिनिटी यहाँ पे है। अब इस केस के अंदर आप एक्सपोज टू एटमॉस्फेयर नहीं है आपका। अब जो फ्लो हो रहा है, आप एक पैसेज के अंदर फ्लो हो रहा है, तो इसीलिए क्या हो रहा, यू आर नॉट गोइंग टू जस्ट लिफ्ट इट। आप सिर्फ लिफ्ट नहीं करेंगे, आप लिफ्ट के साथ साथ वेलोसिटी को बढ़ाएंगे भी, क्योंकि
हाँ
आपका क्रॉस सेक्शन एरिया कम हो रहा है यहाँ पे।
हाँ।
अब बताइए डाउट क्या है।
तो सर वही बोल रहा हूँ कि अगर वेलोसिटी बढ़ रहा है ना,
जी
तो जो इनिशियल केस में वेलोसिटी था,
जी
मतलब जो ये कंपनसेट करने से पहले,
जी
समझो 15 अपना यू मैक्स है वहां
हाँ,
पे जो सेंटर पे। आफ्टर
सेंटर पे नहीं, पूरा
कंपनसेशन,
शुरू से एंडिंग तक यू मैक्स था, यू 15 था। हाँ
हाँ, तो
हाँ,
सेक्शन 2 पे आने के बाद उसका वैल्यू चेंज होगा
बढ़
1
गया।
से।
हाँ
हाँ, तो अभी कंपनसेशन से पहले समझो 15 था,
ओके,
समझे। तो कंपनसेशन के बाद वो बढ़ना चाहिए ना।
बढ़ गया ना।
तो फिर वो जो बढ़े वाला है, मतलब वो डेल्टा के लिए करस्पॉन्डिंग वैल्यू निकालने को कहा, वो 15 वाला चाहिए होगा क्वेश्चन के हिसाब से। मतलब ये डेल्टा के लिए सेंटर पे जो वैल्यू होगा वो कैलकुलेट करना है ना सर अपने को।
सेंटर पे यही वैल्यू होगा, 23.43 रहेगा।
तो सर मैं बोल रहा था कि ये जो गिवन डेल्टा स्टार के लिए करस्पॉन्डिंग वैल्यू होगा सेंटर का।
अरे सर, आप पहले बात तो डेल्टा स्टार का एक्चुअल मतलब नहीं समझे अभी, ठीक है।
ओके।
देखिए ये डेल्टा पे भी सेंटर पे वही वेलोसिटी होगा 23.43। डेल्टा स्टार डेल्टा के अंदर का एक पार्ट है जिसको हम एलिमिनेट कर रहे हैं फ्लो से, समझने के लिए कि फ्लो यूनिफॉर्म है,
हाँ।
ठीक है। तो जितना आंसर ये आया वही आंसर इसके लिए वैलिड रहेगा।
ओके।
ओके ना,
ओके। ओके।
थैंक यू। वेंकटरमन,
Good morning, sir.
गुड मॉर्निंग।
Sir, can you open the last slide?
लास्ट स्लाइड दिस वन।
Yes, sir. Sir, in this, what is mean by that d square u by dy square?
Second differential of velocity, d2 by dy2.
Means
du by d,
means for
you
what?
understand du by dy?
Yes, sir.
Okay. d by dy of du by dy is known as d2u by dy2.
Means what does it means? Means any term for it?
It is representing the slope of velocity. Du by dy is what? Slope of velocity profile. d2u by dy2 is what? Slope of velocity profile. Imagine you are having some velocity profile like this.
Yes, sir.
If velocity profile is like this, then du by dy is going to be constant, correct?
Yes, sir.
Now let us say I draw the graph of du by dy versus y. Du by dy is supposed to be constant. Okay, du by dy is supposed to
Okay,
be
sir.
constant. If du by dy is supposed to be one second. If I draw the graph of du by dy versus y, it is constant. What is the slope of this thing? 0.
Yes, sir.
That is d2u by dy2. d2u by dy2 means second differential of velocity or slope of velocity profile. Okay.
Okay.
Once you differentiate, again you can develop a curve. That curve will be for what? Du by dy. Again, if you differentiate that, you are going to get d2u by dy2. d2u by dy2.
Okay.
Okay, na?
Get
You
it,
try
sir.
a
Thank you,
problem,
sir.
you'll understand that then. ठीक है. Thank
Okay,
you.
sir.
Saurav Kumar.
हेलो.
Hello, tell me.
हाँ, गुड मॉर्निंग सर.
Good morning, tell me.
सर वो आप स्ट्रीमलाइनिंग या बॉडी वाला जो एग्जांपल दिए थे ना, बॉक्स टाइप कार मॉडल,
जी जी जी.
सर वो लाइक आप रिपीट कर सकते हैं डी पी बाई डी एक्स के थ्रू? कैसे उसमें वेट ज़्यादा है?
जी
मतलब आप बोले ना बॉक्स टाइप मॉडल में वेट ज़्यादा होगा.
हाँ, ज़्यादा होगा.
हाँ सर, वो कैसे डी पी बाई डी एक्स बता सकते हैं थोड़ा?
डीपी बाई डी एक्स, देखिए जब गाड़ी फ्लो कर रही है सामने, अचानक से क्रॉस सेक्शन चेंज हो रहे हैं, आप बताइए सडन चेंजेस इन ज्योमेट्री डेंजरस हैं या ग्रेजुअल चेंजेस डेंजरस हैं?
सडन
ये सडन चेंज है कि ग्रेजुअल चेंज है?
सडन है।
हाँ, तो डीपी बाई डी आपका प्रेशर ग्रेडियंट जो है एकदम चेंज कर जाएगा, है ना? ये सडन एक्सपेंशन में चला जाएगा।
सर पर उसके बाद तो फिर एक कांस्टेंट रहेगा ना।
उसके बाद फिर से एक्सपेंशन में जाएगा।
अच्छा मतलब एक केस के
ये
लिए कहना
इसी
चाह रहे हैं।
रीजन के अंदर इतना ज्यादा वेक आ जाएगा, इसी रीजन के अंदर इतना ज्यादा वेक आ जाएगा कि वही बहुत ज्यादा हो जाएगा ना।
वही एक वर्टिकल पोर्शन के लिए।
हाँ वर्टिकल पोर्शन के लिए लीजिए,
अच्छा
ठीक है ना। इसी रीजन में बहुत ज्यादा वेक आ जाएगा। इसीलिए आप देखिए, आप कभी बाइक जब चलाते, वेन एवर यू राइड अ बाइक, तब आपको तेज चलाना हो तो आप अपने आप को श्रग करेंगे नीचे, यानी कि आप अपने आप को स्ट्रीमलाइन करने की कोशिश करेंगे ताकि आपके पास जो है बाउंड्री लेयर सेपरेशन कम हो जाए, ठीक है। ऐसा एनीथिंग एल्स?
और सर ये जो डिस्प्लेसमेंट थिकनेस में
जी,
सर आप बोले कि जैसे हम लोग आगे मूव करेंगे तो यू इन्फिनिटी बढ़ेगा, तो वो कंपेंसेशन की तरह से ना।
डिस्प्लेसमेंट थिकनेस में जैसे आगे बढ़ेंगे यू इन्फिनिटी बढ़ेगा बोल रहा हूँ। वो
हाँ
किस केस में बढ़ेगा? अगर आप इंटरनल फ्लो में हैं तब बढ़ेगा, अगर आप मतलब पाइप के अंदर हैं तो बढ़ेगा,
सर
अगर आप
कंप्रेशन
एक्सपोज टू एटमॉस्फेयर हैं तब नहीं बढ़ेगा।
भी तो मतलब एटमॉस्फेयर में भी केस में तो सर कंपनसेशन की वजह से तो बढ़ना चाहिए।
नहीं, वो ऊपर चला जाएगा। आप मान लीजिए ऊपर में इनफाइनाइट डिस्टेंस है, ऊपर में इनफाइनाइट डिस्टेंस अवेलेबल है, अगर
अच्छा
इनफाइनाइट डिस्टेंस अवेलेबल है तो ऊपर चला जाएगा।
अच्छा सर, इसलिए यहाँ पर फाइव वन इमेजिनरी की तरफ भी यू इन्फिनिटी लिखा है ना।
हाँ, यहाँ भी यू इन्फिनिटी लिखा गया है।
अच्छा ठीक है सर।
सेम यू इन्फिनिटी होगा, जहाँ पे जितना ये था उतना ही होगा।
फिर पाइप फ्लो में कंपनसेशन की वजह से बढ़ेगा।
पाइप फ्लो के अंदर क्योंकि एरिया अब आपके पास एरिया इनफाइनाइट नहीं है, कंस्टेंट एरिया है, इसीलिए बढ़ना चाहिए बीच में।
हाँ ये कंपनसेशन की वजह से ना।
बिल्कुल कंपल्सरी वजह से।
ठीक है, थैंक यू।
थैंक यू। महीप कुमार उपाध्याय।
Yeah, good morning, sir.
गुड मॉर्निंग सर, टेल मी।
Yes, sir, actually, I send you one question on your WhatsApp, sir.
You have sent me a question on WhatsApp. Please
Yes,
excuse me if I'm not able to see the question. Let me know what question you have sent.
sir, a hydroelectric power plant takes in 30 meter cube per second.
1 second, let me see the question once. Can you just send me one more message, just one hi you send me so that you come up. I'm
Yes,
having
sir, definitely, sir. Wait. One second.
mechanical mode 3 more days will take after tomorrow's class.
Yes, sir, I send you.
Send me 1 second. Array, my net is off.
Yes,
Sorry.
sir.
One moment. Okay. Okay, 1 second. A hydroelectric power plant takes 30 meter cube of water through a turbine and discharges it to atmosphere. Okay, the total head loss in the turbine and penstock system is 20 meters. Assuming turbulent flow with kinetic energy correction factor 1.1, density of water being 1000 and acceleration due to gravity 10 meters, that available to the turbine for power generation is how much? Okay. Can you tell me what difficulty you are having in this problem?
So actually, the penstock and turbine head loss, total head loss is given.
Okay.
And again, water reservoir Z2 and Z1 are given. So they are confused, sir, which Z2 minus Z1 I have to take. And next thing is net head, capital H minus small h. So which things I can consider for solving this question, sir?
Okay, fine.
Because efficiency is equal to 1 minus small h by capital H. So I didn't got any efficiency value even. And P actually.
Can you come again? क्या बोल रहे थे आप अभी? You were saying some statement.
So actually, efficiency is equal to 1 minus.
If
If the efficiency is also not given, so.
आप क्या बोले last? That word I did not understand actually.
So actually, the capital H minus small h, I think it was asking, sir.
Capital?
H minus small h, net head law.
No, he is asking me the net head available for a turbine. Okay, net head is asking. Okay, fine.
So that net head is capital H small h, sir.
Ha. Okay. Efficiency is not given. You're saying.
Yes, sir. So that's why I'm not able to
ठीक,
approve that.
efficiency. If he has given you, 1 second. If he has given you that the head loss is equal to 20 meters. If the head loss is equal to 20 meters, okay. 1 second. 1 second, 1 second, 1 second. The net head available to the turbine for power generation is basically HT over here. He is not asking you net head. He's asking you net head available to the turbine. Okay,
sir.
that is HT over here. You are supposed to find out HT over here. Chali, let us write down the data. The value is given as 100. The losses are given as 10 meters per second. The velocity is equal to 2 meters at the exit. The value of kinetic energy correction factor is equal to 1.1. And fine, that's it. Okay. Now, what am I going to do? I'm supposed to find out HT is equal to how much? Kitna head turbine pe hai for it to cause flow, for it to produce power. For this purpose, I'll take some 0.1 over here, certain 0.2 over here. If I take these 2 points, then I can have P1 by gamma plus V1 square by 2G plus Z1 has to be equal to P2 by gamma plus V alpha into V2 square by 2G plus Z2 plus head loss and plus head of turbine I'm supposed to write. Okay. Now P1 by gamma is 0. P2
Yes.
again is 0. Cancel off. V1 square by 2G is 0. The value of Z1 is equal to 100 is equal to alpha is equal to 1.1 into 2 square divided by 20 plus Z2 is equal to 0. H is equal to 20 plus head loss. From here you can get the value of, HT, sorry, not head loss, HT. From here you can get the value of HT. HT has to be equal to 100 minus 20 minus 1.1 into 4 by 20. Can you get me the value of this thing?
Yes, sir.
कितना आ रहा चेक कीजिए. .4 by 20.22.22. This will be equal to 79.78 meters. Check.
Yes, sir.
The answer should be 79.78 meters, correct?
Yes.
Now, what mistake you are doing? I'll tell you the mistake you are doing.
Sir, I'm not considering that alpha, sir, and I'm taking the. Actually, I didn't try this Bernoulli question from.
Okay.
So actually, I tried from something else. P actually is equal to gamma Q into capital S minus small h, from where I want to get in, sir. So
No. Please understand, what you are thinking is this thing. What you are thinking of is this problem. You are thinking of is this problem. Let us say there is a nozzle over here, the thing you are thinking of, correct?
Yes, sir.
That is fine, accepted. But that is the net head available at the exit of nozzle, which is later going into turbine. ठीक है ना?
Yes, sir.
But right now he has not given you that particular case. Nozzle case he has not given you. He has straight away said that there is a pipe connected to the turbine over here. From the turbine, the fluid is exiting.
Yes,
This is
sir.
what he's saying. यानी कि turbine पे कितना head, how much head turbine has taken, how much head her turbine has taken to produce power, he's asking you.
Yes, sir.
So now you'll have to apply Bernoulli. There is no other option for you.
Yes, sir. And sir, how you consider alpha V square? You're not considering alpha in the V1 section, sir.
Achha, because okay, fine, you can write alpha over here also, but I knew that already over here velocity is 0. That
Okay,
is
sir.
why I did not write over there. I did
Okay,
not bother writing over there. Okay?
Okay.
Otherwise, you can write over here also.
Yes, sir.
Okay, na?
Yes. Okay, thank you, sir.
Always think
Yes, sir.
like this. Always think like this.
Yes,
When a flow is taking place, it has to satisfy continuity equation.
yes, sir.
Okay. After continuity equation, सबसे पहले you have to think Bernoulli equation, nothing else. So
Yes, sir.
Bernoulli equation should be in your mind always, especially when head losses are given. Then you have to use Bernoulli equation. If head loss is given, I think head loss is given as 20 meters, no?
Sir,
Huh.
yes, sir. 20 meter.
Whenever head loss is given, always you should think of Bernoulli equation.
Yes.
ठीक है?
Okay, thank you, sir.
Thank you, sir. Anyone wants to ask anything? You can raise your hand.